So, here's something worth thinking about as you settle in tonight. You feel solid. Your body has weight and shape, and it presses down into the bed, firm and real. But almost all of you is empty. Every atom in you is mostly nothing at all. At the center of each one sits a tiny nucleus, and far, far out from it drift the electrons, and in between there is nothing, just empty space, an enormous amount of it. If you could somehow squeeze all that emptiness out of your body, press every particle right up against its neighbors with no gap left, your entire body would shrink to something smaller than a grain of dust. Everything that you are, every atom of it, packed solid, would be almost too small to see. That sounds like a strange and useless thought, but it is not useless at all, because out in the universe there are places where exactly that has happened. Where gravity has squeezed the emptiness out of matter, pressed it down past every ordinary limit, crushed a whole star into a ball the size of a city, and then, perhaps, crushed it further still, past a boundary that ordinary matter is never supposed to cross. Tonight, we are going to travel there, gently, to the densest matter there is, and to a stranger possibility beyond it, a kind of star where matter may break the last rule it has left. If you were here for the night we spent inside a neutron star, this is the next room along, one floor down, into the deep. And if you were not, that is fine too. We will build it all slowly, from the ground up, from the empty atoms in your own hand, out to the most crushed and exotic stuff in the cosmos. You do not need to follow every step. You do not need to hold anything in your head. If you drift off somewhere along the way, that is completely fine. The stars will keep doing what they do, out in the dark, whether or not you are awake. The ideas will still be here in the morning, and so will you. So let's start where the story actually starts. Not with a star and not with a telescope. Let's start with the puzzle of why you are solid at all, because the answer is stranger than it seems, and it is the key to everything that follows. Press your hand against the mattress. It stops. It does not sink through. The bed feels firm, and your hand feels firm, and where they meet, they hold. You take that for granted your whole life. But if atoms are mostly empty space, why don't they just pass through each other? Why doesn't your hand sink into the bed like a ghost through a wall? What is actually holding all that emptiness apart and making it feel solid? The everyday answer is that the atoms bump into each other, and that is true, but it only pushes the question deeper. What makes them bump? They almost never actually touch in the way two marbles touch. What holds them apart is force, not contact. Part of it is the electric force, the negative electrons of one atom pushing against the negative electrons of another, and we spent a whole night on that. But there is a second thing holding matter apart, a far stranger thing, a purely quantum rule with no equal in the everyday world, and it is the thing that will matter most tonight. It is called the exclusion principle, and it produces a kind of pressure that has nothing to do with heat, nothing to do with electric charge, a pressure that comes purely from the deep rules of the very small. Understanding it is the whole secret of how dying stars hold themselves up and of what happens when they finally cannot. The rule was worked out by a young Austrian physicist named Wolfgang Pauli in 1925. It is called the Pauli exclusion principle, and stated plainly, it sounds almost too simple to matter. Certain particles, including the electrons that make up the outer part of every atom, are forbidden from ever being in exactly the same state, at the same place at the same time. No two of them can crowd into the identical condition. Each one must have its own place, its own state, its own slot. They cannot pile up together, cannot all fall into the same lowest arrangement. They are, in a sense, intensely private. Each electron insists on its own room, and no amount of pushing can force two of them to share. Take a slow breath with that, because it is one of the deepest and least appreciated facts in all of physics. This one rule, this stubborn refusal of electrons to share a state, is why atoms have their structure. It is why electrons stack up in shells around the nucleus, layer upon layer, instead of all collapsing down to the bottom. It is why chemistry exists, why atoms have their sizes, why the whole table of elements has the shape it does. And it is why matter takes up room at all. When you press your hand on the bed and it stops, part of what stops it is this. To push the atoms of your hand into the same space as the atoms of the bed, you would have to force their electrons into the same states, and the exclusion principle simply forbids it. The solidity of the world, the firmness of your own hand, rests partly on the fact that electrons will not be crowded. Push on them, and they push back, not because they are hot, not because they repel electrically, but because the deep law of the quantum world will not let them share. That pushing back is called degeneracy pressure, and it is what holds up a dying star. It is worth sitting for a moment with just how empty an atom is, because it makes everything that follows easier to feel. Picture a single atom. At its center is the nucleus. That is where nearly all the mass is, and it is unbelievably tiny. If you blew the atom up to the size of a great sports stadium, the whole roaring bowl of it, the nucleus would be a single small marble, sitting at the very center of the field. That is all. One marble in an empty stadium. And the electrons? They are smaller still, faint flecks, drifting somewhere up in the vast empty stands. Everything else, all that space between, is nothing. Just emptiness. So when you look at your hand, you are looking at something that is almost entirely empty space. A few tiny marbles, unthinkably far apart, with vast gulfs of nothing between them. The chair you might be sitting in is empty. The floor is empty. The whole solid-seeming world is, at bottom, a scattering of specks in a sea of nothing. And yet it feels solid. It stops your hand. It holds your weight. Why? Because the emptiness is not really empty. It is filled with the electrons, spread out, refusing to be crowded, pushing back on anything that comes near. What you feel as solid is not stuff touching stuff. It is force. It is the electrons of one thing pushing on the electrons of another, across the gap, never quite touching at all. You have never actually touched anything in your life, not truly, not surface to surface. You have only ever felt the push. Hold that gently, because it is the whole key to tonight. Matter is mostly empty, and what holds it up, what gives it its size and its firmness, is not solidity, but a rule, the refusal of particles to share. Now, a dying star is the place where that rule is tested to its limit. Gravity comes to collect on all that emptiness. It tries to squeeze the space out of the atoms, to close the stadium down to the marble, and the only thing standing in its way is the electrons, refusing, pushing back. That refusal is degeneracy pressure, and whether it holds or gives decides the whole fate of the star. To see why that matters for a star, you have to think about what a star is fighting, all the time, for its whole life. A star is a war between two things. On one side, gravity, always pulling inward, trying to crush the enormous mass of the star down into its center. On the other side, pressure, pushing outward, holding it up. In an ordinary star like our sun, the outward pressure comes from heat, from the fierce fire of nuclear fusion in the core, burning hydrogen into helium, keeping the star hot and puffed up against its own gravity. For billions of years, the burning holds the line. But it cannot last forever. Eventually the fuel runs low, the fire falters, and when the outward push of the fire fades, gravity, which never rests, never tires, begins to win. The star starts to collapse. What happens next depends entirely on how heavy the star is, and it is here that the exclusion principle steps in. For a star like our Sun, the collapse does not go very far. As the dying core is crushed smaller and smaller, its electrons are forced closer and closer together until the exclusion principle kicks in hard. The electrons refuse to be crowded any further. Their degeneracy pressure rises, pushing back against gravity, and it stops the collapse. What is left is a white dwarf, the exposed, dying core of a star, about the size of the Earth, but holding as much mass as the Sun, so dense that a single spoonful of it would weigh tons. It is no longer burning. It is just a cinder, held up not by any fire, but purely by the quantum refusal of its electrons to share a state. It will sit there, slowly cooling, for longer than the current age of the universe. Our own Sun will end this way, one day, far off. A warm ember, held up by nothing but a rule. For a long time, people thought that was the end of the story, that every dying star settled into a white dwarf, held up forever by its electrons. But a young man on a long sea voyage worked out that this could not always be true. His name was Subramanian Chandrasekhar, and in 1930, at just 19 years old, he was sailing from India to England to study, and he did the mathematics on the ship. He asked a simple question: is there a limit to how much weight the electrons can hold up? And he found that there is. He found that if a dying core is heavier than about 1 and a bit times the mass of our Sun, a value we now call the Chandrasekhar limit, then not even the degeneracy pressure of the electrons can save it. Above that weight, gravity wins anyway. The electrons cannot hold, and the collapse continues, past the white dwarf, down into something far stranger. It is worth pausing on how his idea was received, because it is one of the sadder stories in science. When Chandrasekhar presented his result in England, one of the most famous astronomers in the world, Arthur Eddington, the same Eddington who had measured starlight bending in the eclipse, stood up and ridiculed it. Eddington could not accept that a star might collapse past a white dwarf, and he mocked the young man's work publicly, and his enormous prestige carried the room. Chandrasekhar was crushed, and he eventually left that field of study for years and moved to America. But he was right. He was completely right. Decades later, he would win the Nobel Prize for exactly this work. The limit bears his name, and it tells us that the heaviest dying stars cannot stop at the white dwarf stage. They must fall further, and when they do, something happens to matter that is almost beyond belief. The electrons are driven into the protons, and the atoms themselves are destroyed, and what is left is a star made almost entirely of neutrons. Let that transformation sink in slowly, because it is one of the strangest things that ever happens to matter. When the collapse pushes past the electrons, the crushing is so severe that the electrons are driven straight into the protons of the atomic nuclei. And when an electron and a proton are forced together hard enough, they merge. They turn into a neutron. So one by one, all through the collapsing core, the protons swallow the electrons and become neutrons. The atoms are gone. The empty space inside them is gone. The electron shells that gave every atom its size, gone. What remains is a solid ball of neutrons, packed shoulder to shoulder, touching, with no gaps at all. The emptiness has been squeezed entirely out. This is a neutron star, and it is the densest visible thing in the universe. It is hard to hold in your mind how dense a neutron star is, so let us go slowly. Take a star more massive than our sun. Take all of that matter, more than a whole sun's worth, and crush it down, not to the size of the Earth, like a white dwarf, but to a ball only about a dozen miles across. A whole sun squeezed into the size of a city. The numbers that come out of that are almost comical. A single teaspoon of neutron star material would weigh about 1 billion tons. One small spoonful, as much as a mountain. If you could bring a sugar cube of it to Earth, it would punch straight through the ground and fall toward the center of the planet. The surface gravity is so strong that a pen dropped from a foot up would hit the ground in a fraction of an instant, moving faster than any rifle bullet. A neutron star is matter wound up to a tightness that nothing in your ordinary life can match. And what holds it up? The same rule as before, only now it is the neutrons doing the refusing. The neutrons, like the electrons, obey the exclusion principle. They too refuse to share a state. So as gravity tries to crush the neutron star further, the neutrons push back with their own degeneracy pressure, a wall of quantum refusal, and it holds the line. For most neutron stars, that is where it rests. Gravity pulling in, neutron degeneracy pushing out, balanced, stable, a city-sized ball of pure crushed matter that will sit there, spinning, for billions of years. But you can already feel the shape of the question we are heading toward. If electrons could be overwhelmed by enough gravity, could the neutrons be overwhelmed too? Is there a limit for them, the way there was for the electrons? And if the neutrons themselves finally give way, what on earth is left? We will get there. But first, it is worth knowing that these objects are not just theory. We predicted them, and then we found them, and the finding is a lovely story. The prediction came in 1933, remarkably soon after the neutron itself was discovered, from two astronomers named Walter Baade and Fritz Zwicky. Zwicky was a brilliant, combative, wildly original thinker, often decades ahead of everyone and often ignored. He and Baade proposed that when a massive star dies in a great explosion, a supernova, what it leaves behind at its center, could be a star made entirely of neutrons. It was an astonishing leap, and for more than 30 years, it stayed just an idea. A neutron star is tiny and faint. Nobody thought one could ever actually be seen. The prediction sat there, quietly waiting, for a generation. The discovery, when it came, was an accident, and it came to a young woman who was not looking for neutron stars at all. Her name was Jocelyn Bell, and in 1967, she was a graduate student at Cambridge, helping to run a new radio telescope built to study distant objects called quasars. She was going through the data by hand, mile after mile of it printed on paper charts, and she noticed a bit of scruff, a small, odd signal that did not fit, a faint pulse coming from one spot in the sky, repeating with astonishing regularity, once every 1 1/3 seconds, steady as a clock. It was so regular that at first the team half joked it might be a signal from an alien civilization, and they labeled it, with a wink, little green men. But it was not aliens. Bell found a second one, in a different part of the sky, pulsing at a different steady beat. 2 of them meant it had to be something natural, some new kind of star. What she had found was a neutron star, spinning. A neutron star can spin extraordinarily fast, many times a second, and it sends out a beam of radio waves from its magnetic poles, sweeping around like the beam of a lighthouse. Each time the beam points at Earth, we catch a pulse. These spinning neutron stars came to be called pulsars, and Bell had discovered the first one, hearing the heartbeat of Zwicky and Bod's predicted star, more than 30 years after they dreamed it up. The neutron star was real. It was up there, spinning, sweeping its beam across the Earth once every second or so, a city-sized ball of crushed matter, the ghost of a dead sun. There is a bittersweet note to it, as there so often is. When the Nobel Prize was given for the discovery of pulsars, it went to Bell's supervisor and another senior man, and not to Bell herself, the one who actually spotted the scruff in the data and refused to let it go. The judgment has been argued over ever since. She has spoken about it with remarkable grace over the years, and gone on to a distinguished career, and much later gave away a large prize of her own to help students who face barriers in physics. But when you hear the steady beat of a pulsar, remember it was a young woman going through paper charts by hand who first noticed the heartbeat of a dead star and was left off the prize. So neutron stars are real. We have found thousands of them now. It is worth pausing on how one is born, because it is one of the most violent events in all of nature, and yet it ends in a strange stillness. A neutron star is born in the death of a massive star. For most of its life, that star burns, holding itself up with the fire in its core. But the fire cannot last. In its final days, the star builds a core of iron, and iron cannot burn to release energy. So the fire stops, and in that instant, the core has nothing left to hold it up. It collapses. In less than a second, a core larger than the Earth falls inward, crushing down to the size of a city. The infall is almost unimaginably fast, a good fraction of the speed of light, and then the neutrons form, and their degeneracy pressure suddenly slams the door. The collapse hits that wall and rebounds. A shock wave tears back out through the falling star. That rebound, and a flood of tiny particles called neutrinos, blows the whole outer star apart. This is a supernova, one of the brightest events in the universe, a single dying star that can briefly outshine an entire galaxy of 100 billion others. And at the center of that blast, where the core fell, sits the newborn neutron star, hot and spinning, wrapped in the expanding fire of its own parent. Almost all of the energy of a supernova, the vast majority of it, comes out not as light at all, but as those neutrinos, a burst of them so enormous it is hard to write down. We have even caught them. In 1987, a star died in a small galaxy near our own, and hours before the light arrived, a handful of neutrinos from that death passed through detectors deep underground on Earth. Just a couple of dozen of them, out of an unthinkable flood. But it was the first time we ever caught the neutrinos from a dying star, confirming, in a few faint clicks, our whole picture of how these things are born. A star died, and we felt its ghost pass through the Earth. The people who first imagined these objects deserve a moment too, because the timing is uncanny. In 1932, the neutron was discovered, and almost immediately, a brilliant Soviet physicist named Lev Landau began thinking about stars made of such dense matter. Then Body and Zwicky made their leap about supernovae. And at the end of the 1930s, an American physicist named Robert Oppenheimer, later famous for other and darker reasons, sat down with his students and worked out the real physics of these stars. With George Volkoff and drawing on work by Richard Tolman, he calculated how a neutron star holds itself up, and crucially, that there must be a limit to its mass, just as there was for the white dwarf. Above a certain weight, even the neutrons cannot hold, and the star must collapse into what Oppenheimer, in the same years, was the first to describe in modern terms: a black hole. So the same quiet man sketched both the neutron star's limit and the black hole beyond it on the eve of the Second World War, decades before either was seen. And once we knew neutron stars were there, we found more and more ways to watch them beyond the radio pulses. Many of them live with a companion star and pull matter off it, and that matter spirals down onto the neutron star and heats up until it glows fiercely in X-rays. So we see many neutron stars as X-ray sources, blazing in a light our eyes cannot see, fed by a stream of stolen gas. Sometimes that gas piles up on the surface and ignites in a sudden thermonuclear flash, an X-ray burst, the whole surface of the star briefly exploding. We watch them spin, and we watch them slowly spin down over the years as they shed energy. And now and then a pulsar does something strange. It suddenly speeds up, just a little, in an instant. We call these glitches, and they are thought to be starquakes, or sudden shifts in the superfluid deep inside, the frictionless neutron ocean briefly handing some of its spin to the crust. Each glitch is a tiny window into the strange matter within. We cannot cut a neutron star open, but we can watch it flicker and glow and stumble, and from that, slowly, learn what it is made of. And once we knew they were there, a natural question grew louder and louder. What is it actually like inside one? What happens as you go down, from the surface, into the crushing dark at the center? Because a neutron star is not simply a uniform ball of neutrons. It has layers, like a strange and violent planet, and the deeper you go, the weirder and denser the matter becomes, until, right at the very core, you reach conditions we do not fully understand, conditions where the final rule of matter might just break. So let us go down into one, gently, layer by layer. Imagine sinking slowly through a neutron star from the surface toward the core. It is not something anything could ever really do, but we can do it in the mind, and it is a strange and beautiful descent. The surface is not soft. It is a solid crust, and it may be the smoothest, hardest surface in the universe. The whole star is nearly a perfect sphere. The tallest mountain on a neutron star might be a fraction of an inch high, because the gravity is so fierce it flattens everything. Under that crust, things grow stranger fast. The atoms here are crushed and stripped. Bare nuclei packed together in a rigid lattice, with a sea of free electrons flowing through them. It is a bit like a metal, if a metal were 1 billion times denser than anything you know. Go deeper, the pressure climbs, and the matter starts to do something no one expected, something with a wonderful name. As the nuclei are squeezed closer, they stop being neat little spheres. They begin to merge and stretch into strange shapes, first into long rods, like spaghetti, then into flat sheets, like lasagna. Physicists call this region nuclear pasta, and they mean it. The densest, strongest material in the universe, the layer just above the core of a neutron star, is shaped, we think, like pasta. Rods and sheets of nuclear matter, stacked and folded, so strong that if you tried to break them, they would resist forces beyond anything else known. It is a serious idea with a silly name, and it is real physics. Go deeper still, and even the pasta dissolves. Now you reach the outer core, and here the matter is what gives the whole star its name. It is a fluid of almost pure neutrons, packed together, touching. And this neutron fluid does something astonishing. It becomes a superfluid. That means it flows with absolutely no friction, no resistance at all, a liquid so perfect it can never be slowed. Deep inside a neutron star, the neutrons swirl in frictionless currents that, once started, would flow forever. There may be a superconductor there too, an electrical current with no resistance, tangled through the star. The core of a dead star is not a dull, still cinder. It is a strange quantum ocean, flowing without end, colder in some ways than you might think, and utterly unlike anything on Earth. Let us go back over that descent slowly, because it is worth feeling the whole strange geography of it. Start at the surface, a shell of iron, crushed and bare, harder than anything, a skin of metal 1,000,000,000 times denser than steel. Below it, the atoms give up their electrons entirely. The electrons pool into a sea and flow free. The bare nuclei pack into a stiff lattice, held rigid, a crystal under pressure beyond imagining. Sink further. The crystal grows denser. The nuclei swell with extra neutrons, bloated, straining. And then they begin to touch and merge and lose their shape. This is where the pasta begins. Rods, sheets, tubes and bubbles of nuclear matter folded into one another. The strongest material there is, shaped like something from a kitchen. It would take more force to break a sheet of nuclear pasta than to break anything else known. Sink further still, and the pasta melts into the sea of neutrons. Now there are almost no protons left, almost no electrons, just neutrons, shoulder to shoulder, touching, everywhere. This is the great bulk of the star, a single vast drop of neutron liquid, larger than a city, denser than a nucleus, flowing without friction. It is the same stuff as the inside of an atom's nucleus, but scaled up to the size of a mountain, to the size of a star. And it is cold, in a strange way, not cold to the touch. Its temperature is still enormous, but compared to the wild energies packed into it, compared to how hot it could be, it is quiet. The neutrons are not jiggling with heat the way atoms in a warm room jiggle. They are pressed into their lowest states, held there by the crush, not by warmth. This is the deep difference we met at the very start. A neutron star holds itself up not with heat, but with the cold quantum refusal of its particles to share. It is a hot object that behaves, in the ways that matter, as if it were near the coldest cold there is. Now sink to the very bottom. Below the neutron sea, in the innermost core, we lose our certainty. The pressure here is the highest anywhere in the universe outside a black hole. And here, right here, is where the neutrons may finally give way, where they may be crushed so close that they overlap and dissolve, where the quarks may come loose. We cannot see it. We cannot make it. We can only reason toward it and wonder. The center of a neutron star is one of the last truly hidden places, a room at the bottom of matter that we have not yet been able to light. And then you reach the center, the very heart of the neutron star. And here, honestly, we run out of certainty. We do not know for sure what is at the core of the densest neutron stars. The pressure there is beyond anything we can make or test. Our best theories start to disagree with each other. And it is right here, at the center, that the most exciting possibility lives. Because the neutrons, packed this tightly, may not be able to stay neutrons at all. To see why, we have to look inside a neutron itself. Because a neutron is not the smallest thing. A neutron has parts, and under enough pressure, those parts might come loose. Here is the thing about a neutron. It is not solid, and it is not simple. It is made of smaller pieces, called quarks. 3 of them, to be exact. Every neutron is a bundle of 3 quarks, held tightly together. So is every proton. The quarks come in types, and the ones inside ordinary matter are called up quarks and down quarks. A neutron is 2 down quarks and 1 up. A proton is 2 up and 1 down. That is really what you are made of, at the very bottom. Not neutrons and protons, but the quarks inside them, 3 to a bundle, in every particle of every atom of you. Now here is the rule that matters tonight, the final rule, the one a quark star might break. In everything you have ever seen or touched, the quarks are never free. They are always locked away, sealed inside particles, in little groups, never roaming alone. You cannot pull a single quark out of a neutron and hold it in your hand. Try to pull 2 quarks apart, and the force between them does not weaken with distance the way gravity or electricity does. It stays strong, or even grows. Pull hard enough, and you do not free a quark. Instead, the energy you put in simply makes new quarks, which pair up and seal the wound. The quarks stay hidden, always. This deep rule is called confinement. Quarks are confined, imprisoned, forever inside their little bundles. In all of ordinary matter, in all of your body, in all the visible stuff of the universe, no quark ever runs free. That is the rule. It has held everywhere we have ever looked. But there is a beautiful twist in the rule, and it is the reason a quark star is even thinkable. The force that binds the quarks behaves in a way that is exactly backward from what you would expect. Think about how gravity works, or electricity. The closer 2 things are, the stronger the pull. Pull them apart, and the force fades. The force between quarks does the opposite. When quarks are far apart, the force is fierce, unbreakable, and that is why you cannot pull one out. But when quarks are pushed very close together, the force between them fades. Up close, they barely feel it. Up close, they act almost free. This strange behavior has a name. It is called asymptotic freedom, and working it out won 3 physicists the Nobel Prize. The name is a mouthful, but the idea is simple. Squeeze quarks close enough, and the chains between them go slack. The prison bars soften. The quarks, crowded tight, begin to roam. And now you can see how a quark star might break the rule after all. Confinement says you cannot pull a quark out, because pulling apart makes the force stronger. But a quark star does not pull the quarks apart. It does the opposite. It crushes them together. It squeezes so many quarks into so small a space that they are all pressed right up against one another. And when they are that close, asymptotic freedom takes over. The force between any 2 of them goes slack. No single quark belongs to any single neutron anymore. They all mingle, all press together, all roam through the whole crowd at once. The quarks are not freed by being pulled out. They are freed by being crushed in. The rule is not broken by force from outside. It dissolves from within, under the weight of the star. That is the deep reason the densest place in the universe might be the one place where the quarks come loose. Not because anything pried them apart, because everything was pressed so close that a part lost its meaning. Confinement holds in the thin, ordinary world, where particles are far apart. In the crush of a quark star, the world is not thin. It is packed to the very limit. And there, and perhaps only there, the final rule may quietly let go. But a rule that holds under ordinary conditions can sometimes break under extraordinary ones. And the core of the heaviest neutron star may be the most extraordinary condition matter ever meets. Push the neutrons together hard enough, squeeze them past the point where they can stay separate, and something may give. The neutrons may be crushed so close that they overlap, merge, lose their edges. And when that happens, the quarks inside them may no longer belong to any one neutron. They may spill out, mingle, and begin to roam freely through the whole core, a great sea of quarks no longer sealed into separate bundles. The confinement breaks. The quarks come loose, not 1 or 2, but a whole star's worth, flowing together in bulk. Physicists call this deconfined quark matter, And a star with a core like that, or a star made entirely of it, would be a quark star. Matter that has broken the final rule. Free quarks in the open, held together only by their own crushing gravity. Now the story takes a turn into something even stranger, and the name tells you so, because the next idea involves a third kind of quark, called the strange quark. So far, we have met only two kinds, the up and the down, the ones inside ordinary neutrons and protons. But there are more. There are 6 kinds of quark in all, and the heavier ones do not usually appear in everyday matter because it takes a great deal of energy to make them, and they quickly decay away. The strange quark is the next one up, heavier than the up and the down, and normally it lives only for a flicker in the great particle colliders before vanishing. In ordinary life, you never meet a strange quark. It is too costly to make and too quick to die. But inside a quark star, things might be different, and this is where a beautiful and unsettling idea comes in. In the 1970s and 80s, a few physicists, notably Arnold Bodmer and later Edward Witten, asked a strange question. What if a sea of quarks would actually be more stable, more settled, if it contained not just up and down quarks, but strange quarks too, all 3 kinds mixed together in roughly equal numbers? The reasoning is subtle, but it comes back to the exclusion principle again. Remember that quarks, like electrons, refuse to share a state. If you have only 2 kinds, up and down, you have to stack a lot of them into higher and higher energy states as you pack them in. But add a third kind, the strange quark, and you open up a whole new set of slots for them to fill. Spreading the quarks across 3 kinds instead of 2 can lower the total energy, and lower energy means more stable. This leads to one of the boldest guesses in all of physics. It is called the strange matter hypothesis, and it says something that sounds almost impossible. It suggests that this 3-quark mixture, this strange quark matter, might not just be stable inside the crushing core of a star. It might be stable anywhere. It might be, in fact, the true lowest energy form of matter in the universe, more stable than iron, more stable than anything, which would mean, strangely, that the ordinary matter you are made of, the protons and neutrons, the atoms, all of it, is not the most settled form matter could take. It would mean that ordinary matter is a kind of long-lived accident, and that the real ground floor, the truly stable bottom, is strange quark matter. We would all be living on an upper story, so to speak, held up only because the path down to the true basement is so hard to find. If that is true, and it is a genuine if, then a quark star might not be made of ordinary up and down quark matter at all. It might convert itself into strange quark matter and become what is called a strange star, a whole star of this new, more stable stuff. Its surface would be unlike anything else in the cosmos, not a crust of crushed atoms, but a bare, sharp edge of pure quark matter, held together not by gravity pressing down on it from above, but by the deep force between the quarks themselves, the strong force binding the whole surface like the skin of one enormous particle. A strange star could be a single object, in a sense, one gigantic bundle of quarks, city-sized, bound as tightly as the inside of a single neutron, but scaled up to the mass of a sun. It is one of the most exotic things anyone has ever seriously proposed, and whether any exist is still completely open. Let us sit for a moment with how strange such a star would be, because it is worth the wonder. A neutron star is held together by gravity. Take gravity away, and it would fly apart. A strange star would be different. It would be held together, in part, by the strong force itself, the same force that binds the quarks inside a single particle. It would be, in a sense, one single object, one enormous particle, city-sized, bound as one. You could, in principle, have a lump of strange matter of any size at all, a speck, a boulder, a mountain, a star, all bound the same way, all stable, all made of the three kinds of quark mingled together. Its surface would be like nothing else. A neutron star has that thick crust of crushed nuclei miles deep. A bare, strange star might have almost no crust at all, just a sharp, sudden edge where the quark matter ends and space begins. The density would not fade gently as you rose. It would drop like a cliff, from the densest matter in the universe to empty vacuum in a distance smaller than an atom. The edge of a strange star would be the sharpest boundary in all of nature, and it could be small, smaller than a neutron star. Because it is bound so tightly, a strange star could hold together at sizes and weights a neutron star could not. A very small, very dense dead star, smaller than the rules of neutron matter allow, would be a striking hint. It would whisper that we were not looking at neutrons at all, that we were looking at quarks, set free, holding themselves together in a way ordinary matter never can. None of this is confirmed. It may be that strange matter is not stable, and that no such star exists anywhere, and that the idea, for all its beauty, is simply wrong. That is a real possibility, and honest scientists hold it. But it may also be true, and if it is, then somewhere out in the dark, there are stars made of a substance more stable than anything you have ever touched, with edges sharper than anything you can imagine, holding, in their hearts, the free quarks that all ordinary matter keeps locked away. We do not yet know, and not knowing here is its own kind of wonder. There is a darker corner of this idea, and it is worth telling gently, because it sounds alarming, and it is, in the end, reassuring. If strange quark matter really is more stable than ordinary matter, then a small lump of it, called a strangelet, would be a dangerous thing to meet, because it would be hungry, in a sense. If a strangelet touched ordinary matter, it might convert that matter into more strange matter, releasing energy and growing, and then convert the next bit and the next. In principle, a single stable strangelet falling onto a planet could, the worry went, slowly turn the whole planet into strange matter, a runaway conversion, spreading from a single seed. It is a little like a science fiction idea, a substance that transforms whatever it touches into more of itself. When the great particle colliders were being built, some people worried, quite seriously and publicly, that smashing particles together at enormous energies might accidentally create a strangelet, which might then eat the Earth. It made headlines. It frightened people. And physicists took the question seriously, because you should always take such a question seriously, and they studied it carefully. And the conclusion, thankfully, is that we are safe, and we can be confident of it for a simple and beautiful reason. The Earth and the Moon and everything else in the solar system has been bombarded by cosmic rays for billions of years. These are particles from space that strike us with energies far higher than anything we can make in any collider, and they have been doing so, constantly, since the solar system formed. If such collisions could make a dangerous strangelet, it would have happened countless times already, long ago, and the Earth would have been converted eons before we arrived. But here we are. The Moon is still the Moon. The old, quiet worlds are still ordinary matter. Nature has been running this experiment at higher energies for 4.5 billion years, with no disaster, so the sky itself is our proof that we are safe. Whatever strangelets may be, they are not falling on us and eating the world, and they never have. So we can set the fear gently aside, Strange matter, if it exists at all, seems to keep to itself, sealed in the hearts of dead stars, where the pressure is beyond anything we could ever reach. It is not coming for us. It is a thing that may live only in the most crushed places in the universe, far away, harming nothing, a quiet extreme at the very bottom of what matter can be. And that leaves the real question, the one that actually keeps astrophysicists up at night. Not whether strange matter is dangerous, but whether it is real at all. Are there quark stars out there? Are there strange stars? Somewhere in the dark, is there a star that has truly broken the final rule and set its quarks free? And how would we ever know? That is the hard part. Telling a quark star from an ordinary neutron star is genuinely difficult because from far away they look almost the same. Both are tiny. Both are dizzyingly dense. Both spin and pulse and sit where a dead star should be. You cannot see the difference with your eyes. So astrophysicists look for subtle clues, small tells in the numbers, and there are a few. One clue is size for a given weight. A quark star, if strange matter is real, could be more tightly bound than a neutron star. It might be able to be smaller for the same mass, or to exist at masses and sizes a neutron star could not. So if we ever measure a dead star that is too small, or too dense, or too light, one that does not fit what neutron matter allows, that could be a sign. A star that sits outside the neutron star rules might be playing by different rules. It might be made of quarks. Another clue is the surface. A neutron star has that crust of crushed nuclei. A bare, strange star would not. Its surface would be pure quark matter, sharp and strange, and it might behave differently, cool differently, or fail to do some of the things a crusted star does. A third clue is how fast they spin, and how they cool over time, and how they ring when they are disturbed. Each of these carries a faint fingerprint of what the star is made of. None of them, so far, is a clean answer. But over the years, a handful of observed stars have raised eyebrows. A few seemed oddly small. A few seemed to cool too fast, or too slow. Every so often, a paper appears suggesting that this or that object might, just might, be a quark star. And then more data comes in, and usually the ordinary explanation holds, and the candidate fades. So far, there is no quark star we can point to with confidence, but there is no proof against them either. They sit in the space of the genuinely unknown. The sharpest new way to probe all of this came in 2017, and it did not use light at all. It used gravity. Remember the gravitational waves, the ripples in space-time we can now catch. In that year, for the first time, we detected the waves from two neutron stars spiraling together and colliding, an event called a kilonova, in a galaxy far away. And as those two dead stars whirled closer and closer in their final moments, they stretched and squeezed each other with their gravity, like two water drops distorting before they merge. How much they distorted, how squishy or how stiff they were, left a faint mark on the gravitational waves we caught. And that squishiness depends on what they are made of. So for the first time, we had a direct handle on the nature of ultra-dense matter, read from the trembling of spacetime itself. The measurements so far mostly fit ordinary neutron matter, but they do not rule out that something stranger lives in the densest cores, and every new merger we catch tightens the picture a little more. Underneath all of this sits one great unanswered question, and it is worth naming plainly because it is the real frontier here. Physicists have a phrase for what they are missing. They call it the equation of state of dense matter. It sounds dry. What it really means is simple and deep. It is the answer to the question, what happens to matter when you squeeze it that hard? How does it push back? How dense does it get? What does it turn into? And the honest truth is that we do not know. We can make matter mildly dense in the laboratory. We cannot come anywhere close to the density inside a neutron star's core. We cannot build it, cannot test it, cannot squeeze anything that hard on Earth. So the very center of a neutron star is one of the few places in all of physics where our theories run out, and we are left genuinely guessing. There are several possibilities for what that core is, and quark matter is only one of them. Maybe the core is just very dense neutron matter, ordinary to the end. Maybe the neutrons there transform into heavier cousins, particles called hyperons, that contain strange quarks but stay bound in bundles. Maybe the quarks come loose into a deconfined sea, a quark core inside a neutron shell, a hybrid star. Or maybe the whole thing converts to strange matter and becomes a true strange star. We do not know which. Each possibility makes slightly different predictions about how big the star can get, about the heaviest one that can exist before collapsing into a black hole, about how they cool and spin and merge. And so, slowly, by measuring more and more dead stars, by catching more and more mergers, we are closing in, narrowing the options, learning the rules of the densest matter there is. It is one of the liveliest questions in astrophysics right now, and it is genuinely unsettled, argued over in papers as you lie here in the dark. And there is something wonderful in that. Honestly, something worth resting on. The densest matter in the universe is also some of the least understood. We have crushed our imaginations down to the center of a dead star and found a door we cannot yet open. We know matter has a bottom, a most crushed state, and we know that near it the final rule of ordinary matter, the imprisonment of the quarks, might finally break. But whether it truly breaks, and where, and in how many stars, we cannot yet say. The most extreme place matter can go is still, in part, a mystery, and the people trying to solve it are alive right now, working on it, and they do not yet know the answer. The story is unfinished. It is being written, quietly, in the dark, by people who love it, and they have real tools now, better than ever before, closing in from every side. There is a small telescope on the space station, watching neutron stars in X-rays, measuring their sizes to a precision that would have seemed impossible a generation ago, because size for a given weight is one of the sharpest clues to what the matter is. There are the gravitational wave detectors, listening for the next merger, and the next, each one squeezing the range of what the dense matter can be. There are the great particle colliders, remaking the free quark soup for a flicker, studying how it behaves. And there are the pulsar hunters, weighing the heaviest dead stars they can find, each new heavy one narrowing the answer. Piece by piece, from the sky and from the laboratory, the picture is tightening. We may not have a quark star we can point to yet, but we are learning the rules of the densest matter faster now than at any time before. And it is entirely possible that within the lifetime of someone listening tonight, the question will be settled, that someone, someday soon, will look at a dead star and say, with confidence, that its heart is made of free quarks, that the final rule really does break out there, that a piece of the newborn universe is sealed in the dark, or that it does not, and the neutrons hold to the very end. Either answer would be a triumph. Either way, a door that is closed tonight would open. For now, it stays closed, and that is all right. Some of the best things in science are the doors not yet opened. They are what keeps people looking, and they are a soft place to rest, honestly, because a universe with a few doors still closed is a universe that still has wonders in it, waiting. There is a connection here that is worth sitting with, because it reaches back to the very beginning of everything, and it makes a quark star feel less like a monster and more like a memory. That sea of free quarks, the deconfined quark matter that might fill the core of one of these stars, is not entirely new to the universe. The whole universe was once made of it. In the first tiny fraction of a second after the beginning, everything was so unimaginably hot and dense that quarks could not be bound into neutrons and protons at all. There was no ordinary matter yet. There was only a searing, formless soup of free quarks and the particles that bind them, called gluons, all mixed together, filling all of space. Physicists call this the quark-gluon plasma. It is the state the entire cosmos passed through in its very first moments before it cooled. Then, as the universe expanded and cooled, something happened that is never fully reversed. The quarks came together. They paired and tripled up, sealed themselves into neutrons and protons, and the confinement we spoke of took hold. The free quarks were locked away, 3 to a bundle, and they have stayed locked away ever since, in all the ordinary matter that formed afterward, in every star and world and body. That first free quark soup was gone within the first millionth of a second, and the universe has never gone back, except, perhaps, in one place, the core of a quark star. Because if the quarks come loose there, under crushing pressure, then a quark star would hold, in its heart, a tiny drop of the state the whole universe was in at the dawn of time. Not hot, like the early universe, but cold and crushed, held together by gravity instead of heat. A quark star would be a small, dense echo of the newborn cosmos, a preserved fragment of the first instant, kept alive in the crushed heart of a dead sun. When you look at the possibility of a quark star, you are looking at the possibility that a piece of the beginning of everything is still out there, sealed in the dark, waiting. We have also tried to make that first soup again, on purpose, for the briefest flicker, and we have succeeded. In the great particle colliders, by smashing heavy atomic nuclei together at nearly the speed of light, physicists have created tiny, fleeting droplets of quark-gluon plasma, recreating for a fraction of a second the state of the universe at its birth. It is unimaginably hot, trillions of degrees, the hottest thing ever made by human hands, and it lasts almost no time at all before it cools and the quarks lock themselves away again. So we have met the free quark state twice now, once as the fiery origin of everything, briefly reborn in our machines, and once, perhaps, as the cold and crushing heart of a quark star, the hottest place and one of the coldest, dense places in the universe, holding the very same thing, the quarks set free. So how might a quark star actually come to be? There are a few gentle ideas, and they are worth walking through slowly. The simplest is that it happens in the same breath as a neutron star is born. When a massive star dies and its core collapses, if that core is heavy enough, the crush at the center might go straight past the neutron stage and deconfine the quarks then and there in the first instant, so that the star is born as a quark star or as a hybrid with a quark core from the very start. In that picture, some of the dead stars we call neutron stars might secretly have quark hearts, and always have, since their violent birth. A stranger idea is that a neutron star might turn into a quark star later, suddenly, long after it forms. Imagine a neutron star sitting quietly, spinning, cooling, for millions of years. Now imagine it slowly gaining a little mass, perhaps by pulling matter from a companion star, or simply slowing its spin so that it can no longer resist its own gravity. At some critical moment, The core crosses the threshold. The neutrons give way. The quarks deconfine all at once in a runaway that races outward through the star. In a heartbeat, the neutron star converts itself into a quark star. And that conversion would release a tremendous burst of energy, a flash of light and particles, as the matter drops to its new, more stable, lower energy state. Some physicists have wondered whether certain mysterious, intense bursts we see in the sky, sudden flashes we do not fully understand, might be exactly this: the moment a neutron star becomes a quark star, a dead star, quietly changing its very nature and announcing it with a flash we can see across the universe. It is not proven, but it is the kind of idea that makes people keep watching the sky. And once a quark star exists, it would be one of the strangest stable objects in the cosmos. Picture it: a ball only a dozen miles across, holding more than a sun's worth of matter, made of quarks no longer bound into particles, flowing free. If it is a true strange star, its surface would be a sharp edge of pure quark matter, bound by the strong force, unimaginably smooth and unimaginably strong. It might spin hundreds of times a second. It might be a little smaller, a little denser than any neutron star could be. And in its heart, that drop of the beginning of the universe, the free quarks, the broken rule. It would be, in every sense, matter pushed to its final extreme, one step past the densest ordinary star, one step short of the ultimate collapse. Because there is one more step down, and it is the last one of all. Before we take that last step, there is one more strange thing the quarks might do, deep in the core, and it rhymes with something we met on the night about heat. Remember superconductivity, where electrons in a cold metal pair up and flow with no resistance at all. The quarks in a quark star, packed and cold and dense, might do something similar. They might pair up too, and when they do, they can form exotic phases of matter with strange and lovely names. One is called color superconductivity. Another, the most ordered of all, is called color flavor locked matter, where the quarks arrange themselves into a deep, symmetric pattern, all the kinds locked together in a single elegant order. You do not need to hold any of the details. The point is gentler than the names. It is that the core of a quark star might not be a formless soup at all. It might be a highly ordered quantum perfect state, a kind of crystal of quarks, flowing without friction, arranged with a symmetry more perfect than anything we can build. The most crushed matter in the universe might also be, in its own way, the most orderly. There is something beautiful in that. At the very bottom of the crush, past the point where atoms and even neutrons give up their shapes, the quarks may settle into a new and quiet order of their own. Not chaos, a different kind of calm. We do not know for certain that any of these phases exist in real stars. They live, for now, mostly in the mathematics. But they show how rich the bottom of matter might be, how many strange rooms there may be down there, below the last door we have opened. So we have come a long way down. From ordinary atoms, mostly empty, held apart by the refusal of electrons to share, down to the white dwarf, held up by that same refusal, crushed to the size of the Earth. Down past the Chandrasekhar limit to the neutron star, where the atoms are gone and a whole sun is squeezed into a city, held up by the neutrons refusing to share. Down, perhaps, to the quark star, where even the neutrons give way and the quarks come loose, and the final rule of confinement breaks. At each step, gravity pushes harder, and matter finds a new, deeper way to resist. But there is a last step, and at the last step, matter runs out of ways to resist, because gravity, in the end, does not tire, and matter does. Add enough mass, and nothing can hold. Not the electrons, not the neutrons, not the quarks, free or bound, ordered or not. There is a heaviest a dead star can be, and above it, no pressure of any kind is strong enough to stop the fall. Gravity wins completely, and finally, the matter collapses and keeps collapsing, past the quark star, past every state we know or can imagine, down and down with nothing left to stop it, until it vanishes behind a horizon and becomes a black hole. That is the true end of the ladder. A place where matter as we understand it simply ceases, crushed out of existence, or into a state we have no theory for at all. So a quark star, if it exists, sits at a very particular place in the story of matter. It is the last stand. It is the densest that matter can be, while still being matter, still being stuff made of particles you could name, still holding itself up against the crush. One step further, and it is not matter anymore. It is a black hole, and the rules go dark. The quark star lives right on that final edge, at the very bottom of what can still be called a star, the most extreme thing that has not yet fallen over the cliff into a black hole. It is matter, standing at the door of oblivion, having broken every rule it can break, holding on by the last thread it has, the free quarks themselves, pressed together, refusing still to give the final inch. And these dead stars, before some of them fall over that edge, do one last generous thing, and it reaches all the way to you. When two neutron stars spiral together and collide, in the kind of merger we caught with gravitational waves in 2017, they fling out a spray of their crushed matter into space, and as that ultra-dense neutron matter suddenly decompresses, it undergoes a furious burst of nuclear reactions, and it builds the heaviest elements there are. Gold, platinum, much of the silver and the rare earths. The heavy, precious metals of the universe are forged, we now believe, in large part, in the collision of dead stars. The gold in a ring, the platinum in a wire, was very likely made in the merger of two neutron stars, long ago, before the Earth existed, and scattered into the cloud that became our world. So the densest, strangest, most crushed objects in the cosmos are also the makers of some of the most beautiful and lasting things in it. And a little of that gold, made in the death of stars, may be closer to you than you think. There is a number at the heart of all this that people are chasing hard right now, and it is worth knowing about, because it is where the quark question may finally be settled. It is the heaviest a neutron star can be. Every neutron star has a top weight. Below it, the star holds. Above it, gravity wins, and it falls into a black hole. This top weight is called the maximum mass, and it is not just a curiosity. It is a fingerprint of what the star is made of. Here is why. A star made of stiffer matter can hold more weight. A star made of softer, squishier matter gives way sooner. So the heaviest neutron star that can exist tells you how stiff the matter inside really is. And that, in turn, tells you whether the quarks come loose, and when. If matter turns to quark matter in the core, it tends to soften, and the star cannot hold as much. So the maximum mass is a clue to the quarks. So astronomers hunt for the heaviest neutron stars they can find, and they weigh them carefully using the orbits of their companion stars. The heaviest ones we have found so far are around 2 times the mass of the Sun, and a little more. Each new heavy one we find raises the floor of what the matter must be able to hold, and each one narrows the options for what lives in the core. A very heavy pulsar rules out the softest kinds of matter. A merger that collapses too easily rules out the stiffest. Slowly, from both ends, the answer is being squeezed. There is a razor's edge here, and it is beautiful. A neutron star sits just barely on the safe side of becoming a black hole. It is the last thing that can hold. Push it a little past its limit, and there is no next kind of star to catch it. It simply falls. So every neutron star we see is a survivor, matter that found a way to hold, right at the edge of the cliff. And a quark star, if it exists, would sit even closer to that edge, the very last foothold before the drop. And here is one more strange thought, before we turn to the magnets. Some of that strange quark matter, if it is real, might not only live in stars. Small lumps of it, those strangelets, might be drifting through space on their own. And a few physicists have wondered whether such lumps could be part of the dark matter, the unseen stuff that makes up most of the matter in the universe, whose nature is one of the great mysteries. Probably not. There are good reasons to doubt it. But it is a lovely possibility to hold, that the missing mass of the cosmos, the dark stuff we cannot see, might be, in part, tiny nuggets of the same broken rule matter that fills the hearts of dead stars. We do not know. It is one more open door, one more strange possibility drifting quietly in the dark, waiting for someone to work it out. And there is no shortage of them in this corner of physics. The deeper you go into matter, the more doors there turn out to be. Now, before we leave these dead stars and come home, there are two more wonders worth resting on, because they are among the strangest things in the sky, and they are gentle to fall asleep to. The first is about magnetism. Some neutron stars have magnetic fields so strong they are almost beyond belief. We call these ones magnetars, and they hold the most intense magnetic fields known anywhere in the universe. How strong? Strong enough that if a magnetar sat where the moon sits, its field would wipe the data from every credit card on Earth and reshape the atoms in your body. Get close to one, closer than a few thousand miles, and the field would be so strong it would tear you apart, not with heat or force, but by distorting the very shape of your atoms, stretching them thin. The atoms in you can only hold their shape in a normal field. Near a magnetar, they cannot. A magnetar is a neutron star with a field trillions of times stronger than the Earth's. And that field is not quiet. It shifts and strains, and now and then it snaps. When it does, the crust of the star cracks, a starquake, and the magnetic field reconnects in a violent instant, and the magnetar lets out a flash of energy so bright it can be detected across the galaxy and beyond. In 1979, and again in 2004, flashes from magnetars washed over the Earth from thousands of light years away, and they were strong enough to disturb our instruments and the upper edge of our atmosphere from that enormous distance. A single such flash can release, in a fraction of a second, more energy than the sun puts out in many thousands of years. And it comes from a crack in the crust of a dead star, a city-sized ball, far away in the dark. These are real. They are up there now, spinning, straining, waiting to crack. The second wonder is about time. A pulsar, spinning and sweeping its beam, is a clock, and it is a magnificent one. The fastest pulsars spin hundreds of times every second, and their pulses arrive with a regularity that rivals the best atomic clocks humans have ever built. A dead star, wound up by its collapse, keeping time across the galaxy to a precision of billionths of a second, steady for years and years. We use them as clocks. We use them to test the deepest ideas in physics, because their timing is so exact that even the faint bending of space around them shows up in the beats. And we have begun to use whole networks of them, spread across the sky, as a single vast instrument. By watching many pulsars at once and looking for tiny shared shifts in their timing, We can feel the slow swell of gravitational waves passing through the entire galaxy, ripples so long and low that they take years to wash past. The dead stars themselves have become our detectors, a galaxy full of spinning corpses, ticking, and in their tiny stumbles we read the trembling of the universe. There is something quietly beautiful in that. The things that die most violently become the steadiest clocks we have. So gather it all up now, gently, the whole family of crushed and dying stars, and hold it lightly as we begin to come home. Think of what matter does when gravity truly leans on it. First it holds, in ordinary atoms, kept apart by the refusal of electrons to share, the same refusal that makes your own hand solid tonight. Then, in a dying sun, it gives a little and settles into a white dwarf, an Earth-sized ember held up by that refusal alone. Then, if it is heavy enough, it gives more, past the Chandrasekhar limit, and the atoms themselves are destroyed, and a whole sun is crushed into a city of neutrons, spinning, magnetized, ticking like a clock. And then, perhaps, at the very bottom, it gives one last time, and the neutrons dissolve, and the quarks come loose, and matter breaks its final rule, and becomes a quark star, a drop of the newborn universe held in the dark. And one step further than that, there is no holding at all, only the black hole, and the end of what we can know. It is a kind of ladder, going down, and at every rung, matter finds a new and deeper way to resist, a new inner strength you would never have guessed was there, until gravity finally finds the one below it. We have climbed most of the way down that ladder now, in our understanding, and we are standing near the bottom, peering at the last rungs in the dark, not quite sure what we are seeing. The quark star, if it is real, is nearly the last thing matter can be, before it stops being matter at all. And whether it is real, whether the final rule truly breaks out there somewhere, is a question still open tonight, held by people who are alive right now, and who do not yet know. There is something restful in standing at that edge, honestly. We have followed matter down as far as we can, past the atom, past the neutron, nearly to the quark, and found, at the bottom, not an answer, but a door we have not yet opened. The densest, strangest matter in the universe is still partly a mystery, and that is not a failure. It is just how far a young species has managed to see, staring down into the crushed hearts of dead stars from a small, warm world very far away. So let us leave the question open, where it belongs, and turn now, and begin the long, slow climb back up the ladder, out of the crush, back through the wide dark, home to the room, and the bed, and the quiet, empty, solid-seeming body lying in it. Before we come all the way home, let us do one last gentle thing. Let us go near one, in the mind, and simply look, not to land, just to draw close and see what there is to see. It is a strange and quiet place to visit on the way to sleep. So imagine we are far out and drifting closer. From a distance, a neutron star is almost nothing to look at. It is tiny, 12 miles across, smaller than a city. If it were not so hot, you could not see it at all. But it is hot. Newborn ones glow. And it spins, fast, sometimes many times a second, far too fast to follow. Come closer. The first thing you notice is not the star. It is what the star does to the space around it. The gravity is so strong that it bends the light nearby. You can see a little too much of the star. Its far side is bent into view, curving around the edge, so you seem to see more than half of it at once. The background stars behind it are smeared and shifted. Space itself is visibly warped, like looking through a lens made of gravity. Come closer still. Time begins to change. Near a neutron star, gravity is strong enough that time itself runs slower, measurably, the way it does near a black hole, only less. A clock on the surface would tick noticeably slower than your clock. If you watched the surface from a safe distance, everything on it would seem to move a little sluggishly. And if someone on the surface could look back out at the universe, they would see it running fast, hurried, the far stars wheeling by. Look at the surface now. It is smooth, impossibly smooth. The gravity is so fierce that nothing can stand up against it. The tallest mountain is a fraction of an inch. The whole star is a nearly perfect sphere, polished by its own weight, the smoothest solid surface that exists anywhere. And it is not still. It shivers. The crust is under unimaginable strain, and now and then it cracks, a starquake, and the whole star rings like a struck bell. For a few moments, in waves we can sometimes catch. Do not go down to it. You could not. Long before you reached the surface, the tides would take you. The gravity at your feet would be so much stronger than at your head that you would be stretched, pulled long and thin, the way a black hole would do it, only beginning sooner. Nothing soft can survive near one of these. Nothing made of atoms can hold its shape. The star is a place that unmakes anything that comes near, gently at first, and then not gently at all. And yet, from a safe distance, it is beautiful. A small, bright, perfect ball, spinning in the dark, bending the light around it, sweeping its beam across the sky, keeping time to the billionth of a second. A dead star, and one of the most exquisite objects in all of creation. Let it turn there, in your mind, far away, harming nothing, keeping its ancient rhythm. And let us leave it, and come home. Because the thing worth carrying from all of this is not the star. It is what the star tells you about yourself, lying here. The same rules that build that impossible object build you. The refusal of particles to share, the strength hidden in matter, the deep laws that hold things together against the pull of everything. They are in the star, and they are in your hand on the blanket, and they are the same laws. You do not have to go to a neutron star to touch the deepest physics there is. It is already in you, holding you together, this very moment, in the dark. So let the people we met tonight drift off now, one by one, the way you let go of a day. Wolfgang Pauli, who found the rule that no two electrons will share a state, the rule that makes your hand solid. Chandrasekhar, 19 years old on a ship, working out the limit that a dying star cannot cross, and mocked for it, and right all along. Bode and Zwicky, dreaming up a star made of neutrons long before anyone could see one. Jocelyn Bell, going through her paper charts by hand, finding the heartbeat of a dead star, and left off the prize. Bodmer and Witten, wondering if strange matter might be the true floor of everything. You do not have to keep their names. Let them go. They did the work so the understanding would exist, not so that you would have to carry it. And let the confusion settle too, gently, because it was never a problem to solve before you could rest. We do not know what fills the heart of the densest stars. We do not know if quark stars are real. We do not know if matter truly breaks its final rule out there, or where, or in how many. We do not know the deepest state of crushed matter at all. These are open questions, out in the dark, held by people who love them, and not one of them needs anything from you tonight. Let them stay open. They are a soft place to lie down, so let's come home now, slowly. Back up the long ladder, out of the crush. Leave the black hole at the very bottom, where the rules go dark. Leave it there. Come up past the quark star, that drop of the newborn universe, its free quarks flowing in the dark. Come up past the neutron star, spinning, magnetized, ticking like a clock, a whole sun crushed into a city. Come up, out of the deep, into the wider dark, where the dead stars grow small and faint behind you. Come up through the galaxy now, slowly, past the dead stars, the pulsars sweeping their beams, the magnetars straining in the dark. Let them fall behind, past the living stars, the ordinary ones, still burning, still holding themselves up with their fire, the way our own sun does. They have not died yet. They are not crushed. They are warm and bright and whole. Come past the great clouds where stars are born, vast and dim, slowly gathering themselves in the dark. Come past the crowded lanes of the galaxy, the hundreds of billions of stars wheeling slowly around the center. It is a long way, and there is no hurry. Let the crushed stars grow small and faint behind you. Let the whole strange ladder of matter, the white dwarfs and the neutron stars and the quark stars, sink back into the dark where they belong. Come inward, toward one ordinary yellow star, out near the quiet edge of the galaxy. Nothing special about it. One of billions. But it is ours. And around it, a small family of worlds turning in the dark. Come to the third one, the blue one, the only one, as far as we know, with anyone on it awake and wondering about crushed stars. Come down through the thin skin of its air, the little band of atmosphere that holds all the weather and all the breathing there has ever been. Down to the night side, the half turned away from the star, where it is dark, where you are, down to the land, to the region, to the town, to the street, to the roof over your head, and in through it to this room, to the bed, to the covers, to your own body lying here, quiet in the dark, at the end of the long way home. You have come all the way down from the crushed heart of a dead star and all the way back to the soft and ordinary weight of yourself on the mattress. There is nowhere further to go. You are home, and rest there. You have come all the way down and all the way back, from the crushed heart of a dead star to the soft weight of your own body on the bed. Feel that weight now. Feel the mattress under you. Feel the covers over you. Feel where you are heavy, where you are held, where you are still, and breathe, slow and easy. Feel the air move in and out. There is no hurry now. There is nowhere to be. And feel, underneath it all, the strange thing we started with. You are almost entirely empty. Every atom in you is mostly space, a scattering of tiny marbles in empty stadiums, all through you, everywhere. You are, at bottom, far more nothing than something. And yet you do not fall through the bed. You do not sink through the floor. You hold your shape. You keep your place. Why? Because of the rule. The same rule that holds up a white dwarf, that holds up a neutron star, that decides the fate of every dying sun. The refusal of your electrons to share their states. It is holding you up right now, this instant, keeping your empty atoms apart, making you solid, keeping you exactly here. The thing that holds up a dying star is the thing that holds you on the bed. It is the same rule, the same deep law, in the crushed heart of a neutron star and in the palm of your hand, the very same refusal, holding everything in its place. It has never once let go. Not for a moment of your whole life. It will not let go tonight. While you sleep, it will hold every atom of you exactly where it belongs, without effort, without pause, asking nothing. You are held by the deepest rule there is. You always have been, and the matter you are made of has been all the way down that ladder, or nearly, in other places and other times. The atoms in you were made in stars. The heavier ones, the calcium in your bones, the iron in your blood, were forged in stars that died. And some of the very heaviest, a little of the gold, the trace metals, may have been made in the collision of two neutron stars long before the Earth existed, flung out into space, gathered into the cloud that became our world, and finally into you. You carry in your body a few atoms that were born in the merger of dead stars, in the very kind of crush we visited tonight. You are not separate from any of it. You are made of the same quarks, locked safely into their neutrons and protons, 3 to a bundle, keeping their rule, holding their shape, so that you can lie here and hold yours, and think gently of what that means. The gold in the world was made in the collision of dead stars. The iron in your blood was forged in a star that died. The calcium in your bones. The oxygen you are breathing, slowly, in and out. All of it was made in stars, and scattered when they died, and gathered again over billions of years into the cloud that became the sun and the earth, and in time, you. You are made of the ash of ancient stars. That is not a poem. It is just the history of the atoms lying in this bed. So the story we followed tonight, all the way down to the crushed hearts of dead stars, is your own story too. From the other end, the same matter, the same quarks, 3 to a bundle, keeping their rule, the same deep laws, holding it all together. You are not a visitor to that vast, strange universe of neutron stars and quark matter. You are made of the same stuff, playing by the same rules, resting now in a gentler arrangement of it, for a little while, in the dark. So there is nothing you need to do now, and nothing you need to hold. The dead stars will keep spinning, out in the dark, whether or not you picture them. The quarks in you will keep their bundles, keep their rule, hold you together, without a single thought from you. The exclusion principle will keep your atoms apart all night, keep you solid, keep you here, asking nothing. It will all carry on exactly as it always has, whether you follow it or not. It will still be here in the morning, the whole ladder of matter, the crushed stars, the open questions, and so will you, held together by the deepest rules there are. You do not have to remember any of it. There is no test in the morning, no need to recall a magnetar from a pulsar or Chandrasekhar's limit, or which quark is which. Let the names go. Let the numbers go. The 1,000,000,000 tons in a spoonful, the 12 miles across, all of it, out of your hands. It was never yours to carry. It was only something to listen to on the way down into sleep. All that is left, the only thing being asked of you now, is to lie here and be what you already are. A body, mostly empty, held perfectly solid by the deepest law there is, made of ancient matter, resting in the dark. Let the crushed stars go now. Let the neutron star go, spinning in the dark. Let the quark star go, with its free quarks and its broken rule, if it is out there at all. Let the black hole go, at the very bottom of the ladder, where the rules go dark. Let them all drift off to the edges of the night. They are far away. They are not here. They need nothing from you. Let the questions go too. Whether quark stars are real, what fills the heart of the densest matter, whether the final rule truly breaks somewhere out in the dark. Let them stay open, out there, where they are happy to wait. There is no answer due tonight. There is no test in the morning. And let the numbers go. The 1,000,000,000 tons in a spoonful, the 12 miles across, the mass of the sun crushed into a city. All of it, out of your hands. It was never yours to carry. It was only something to listen to, on the way down. So let your breathing slow. Let your empty atoms hold, faithful and unforced, without your help. Let the dead stars spin on, far away, needing no witness, asking nothing. There is nothing to do but rest here, solid and whole, in a quiet, dark room, one small, held-together thing, in a universe that knows how to crush whole suns and chooses, here, to simply hold you. Feel it one more time. The weight of you on the bed, the covers holding your warmth, the slow, easy rise and fall of your breath, and under all of it, quiet and faithful, the deepest rule there is, holding every empty atom of you exactly in its place. It held the dying stars. It holds you now. It will not let go. The room is dark. The bed is holding you. The rules that hold you are holding everywhere, the way they always have, and you do not have to help them, or understand them, or stay awake for any of it. You only have to lie here and be held. Let the deep rule do its quiet work, the way it always has, the way it always will. Let yourself be solid. Let yourself be whole. Let yourself be held all the way down to the very bottom of matter. So just rest now. It will all still be here, and so will you. Good night.